这种我知道，
啊？
也是东西的。
怎么做这个？那个
是不？
好像有点暗，金康照一反光越来越厉害。啊，
我也是有点。
又不关灯又不可以，那应该可以啊。那2张没有就可以了，那整排都没有，对不对？你讲什么？
之前前面放一排一下，可以打，就是
啊啊，是哦。 嗯，哦，啊，没有，想想从前面睡到后面去了。我们昨天有做什么事情？啊，到几点？ 点啊8点，今天下午，今天下午啊，几点结束？OK 啊，9点了。我还没补这样久，还没有补完还没补片
我们之后还有3个星期。
啊，整个时间在补课。
对对，这样。
哦，对后下个是下个吗还是下下？嗯，OK。那么你的面包放没有啊？
很贵吗？3块钱。Okay. Good day, everyone. We should start the lectures today. During tutorial time, we will discuss the quiz from quiz 3, and then we move our quiz 4 in the second last week, combined with quiz 5. So the test will be all the way from partial ordering. So I think the question is very similar to the exam question. It's kind of a mock exam for you. Any question? Any question for quizzes or lectures or tutorial? So today I'll sit here to give the lecture. Okay. You can see me there, or if you want to see me, you can call me. Because here is too dark. I think my eyesight getting worse. So I should do something. Okay. Okay. Okay, sure. Let's start. So today we will continue the Euler's formula, and then we try to prove the Euler formula and see how this Euler formula comes about. So let's recall what's the Euler's formula. So first you start with a connected planar simple graph. So remember what a planar graph is? It's a graph that has a representation that doesn't have edge crossing. Okay. So let E be the number of edges and V be the number of vertices and R be the number of region. So who remember how these three numbers get biased together? What's the formula? Anyone remember what's the formula between the R, E, and V? What's the formula? What's the formula? R equals to E minus V plus 2. Okay. So you can see that actually this is an alternating sum. Okay. So you can see that vertex is a point, and then H is a line, and then R is a bounded area. So you take your area minus the line plus V is equal to 2. Okay. So you got an alternating sum of decreasing dimension. So this is not a coincidence, but it's a decreasing dimension with an alternating sum, plus minus plus. So you can imagine that you can keep going on, minus plus, and then get higher dimensional object. But anyway, so let's see how this theorem comes about. Okay, proof sketch. So let us start with a planar representation of G. Okay, because it's planar, so we can find a planar representation of G, like what we did last time. Okay, 2 is to construct a sequence of subgraph. How do you construct it? I haven't tell you. We should imagine a sequence of subgraph G1 up to a number maybe GP. Okay, where the last GP is the G. So what we did is successively add H. Okay, at each step. So G1 can be any H of G, and then at each step, Gn, you should add one edges, one edge that is incident with a vertex that appear before. Okay, appear at a previous step. And if in the case that the other vertex is not in there yet, so you should add it in as well, together with the other edge. But don't worry, I will show you one example of what this means. In the GN. By the way, I start uploading the lecture videos now because every one of you is back. Previously, the management don't want to pull out because they want everyone to come back to the physical study. I put out the lecture recording on the Moodle. Okay, so so for example, I hope you can see it. So for example, if our graph is something like this. Okay, so this is our G. This is our G, for example. Okay, so G1, you can start at any edge. Okay, so maybe I start at the top right edge. Okay, any edge of G. So whenever you add an edge, definitely you need to add the vertex in. Okay, so this is a graph. And then G2, what you can do is add another edge such that that edge has is incident with the edge the vertex in the previous graph. So either you can add the right one or the left one. Okay, doesn't matter. So let's say we add this one. Okay, when we add this edge, the vertex is not in the previous graph yet. previous subgraph yet, so we need to add the vertex in. Okay. So next, we can keep going on and then construct G3. And then G3, maybe we choose to add this X here. Okay. But this X here, you already have the both vertex appear before, so you don't need to add a new vertex. Okay. And then you can keep going on, add all the vertex in until you get the whole G. Okay. So in this case, your GP is how many? 1, 2, 3, 4, 5, 6, 7. So you will stop at the 7th stage. Okay. Everyone following the sequence of subgraph. Okay. So every step we just add one edge. So next. So we will prove this theorem by induction. So induction, we start from base case. Okay, so what's base case? Base case is G1. So how G1 looks like is a 2 vertex with 1 edge. Okay, how many region bounded by this graph? How many region? 1. Okay, so there's only one region here. Okay, so R equals to 1, E equals to 1 edge, V equals to 2. Okay, so R equals to E minus V plus 2. So E equals to E minus 2 plus 2, which is okay. So the formulas fall for G1. Okay. So now let's do the inductive step. Inductive step. Inductive hypothesis first. So suppose the formula hold for GK. Okay. And then we want to show that it is true for GK plus 1. Okay. So let me ask you, what's the difference between GK and GK plus 1? What's the difference between GK and GK plus 1? H difference. Okay, so from GK, you add an H to go to GK plus 1. Okay, right? So there are two cases, right? Either when you add the H, the other vertex is not in there. And whether when you add an H, both vertex is already in the previous subgraph. Okay. So there are two cases to consider here. So there are two cases to consider. There are two cases to consider. So case 1, new H with new vertex. Okay. Case 2, new H with pre-existing vertexes. Okay, there are two cases to consider. So new H with new vertex in your mind should be something like this. Okay, new H with new vertex. New H with existing vertex is something like this. Okay, you join the two previously existing vertexes. Okay, make sense? Makes sense. Okay. So let's see let's look at case 1 first. Okay, what's case 1? So in case 1, does the number of region increase or not? No, right? Okay, so the RK plus 1 is equal to RK. Yeah, so the number of region doesn't increase. How about EK plus 1? What's the how's the changes? Plus 1, okay, plus 1 to the previous number of edges. How about VK plus 1? Do you have new vertex? Yes, okay. So you add by how many? 1. Okay, good, very good. So now we want to show that RK plus 1 equals to EK plus 1 minus VK plus 1 plus 2. Okay, this is how we want to show. So let's start with RK plus 1, right? So we got RK plus 1 equals to RK, which is by construction. So these three we are by construction. Okay. This is how we construct these cases. So RK equals to what? Huh? What is RK? Huh? Wow. Okay, very good. EK minus VK plus 2. Okay, so why? Formula? By the inductive hypothesis. Because this formula hold at the GK stage. Okay, yeah, very good. So this one is by inductive hypothesis. Okay, then since we already know EK and EK plus 1, then we can substitute EK and VK using in terms of EK plus 1 and VK plus 1. So EK is equal to EK plus 1 minus 1 minus VK plus 1 plus 2, right? So it's equal to EK plus 1 minus 1 minus VK plus 1, 1 plus 2. This one also by construction. Then is equal to EK plus 1 minus VK plus 1 plus 2. Yeah, make sense? Okay, so it holds for case 1. How about case 2? What's the number of region change after adding an H? Add 1. Okay, you can see that this line add a boundary to the region, so you split it into 2. Okay, so it become RK plus 1. Number of edges also plus 1. Okay, because we add a new edge. But number of vertex change or not? No, right, because we didn't add a new vertex. Okay, good. So you can see that this plus 1 here move to the region. Okay. So if you do the similar computation, you will get the same result. You can try and do it. Okay. Okay. So you can see that this plus 1 here will become the plus 1 here, so that you can cancel it out. Is it okay? Can do it yourself. Okay. So you can see that actually this formula here actually come from a simple observation here. Okay. So it really come from a simple observation on these 2 dots with 1 line. Okay. And then another key is your graph is planar. Okay. So there's no edge crossing like this. You can imagine that when you have edge crossing, you can have extra region, which you cannot control. Okay, but with planar, you can. There's some controlling there. Okay, that's why this formula will help. Okay, so whenever you forgot the formula, you can come back and compute this simple case here. Okay, so make sure these three numbers you know they agree. How they agree, you just need to add a 2 here. Make sense? Make sense? From this graph, you can get these three numbers, but you want these three numbers to agree, you just get a 2. But this minus here, you need to remember. Remember the dimension thing? 2, yeah. Remember this dimension with the alternating sum. Okay. So you got the 2-dimensional at minus 1-dimensional at 0-dimensional. Plus, minus, plus, alternating sum. 2, 1, 0. Yeah. 2, 1, 0 dimension. Okay. All right. Any question on the proof? Question on the proof? No. So there are three corollary we can make from this Euler formula. So the first corollary is G similarly a connected. Connected meaning we don't want to consider like two connected components. We just want to consider one connected component of graph. If G is a connected planar simple graph with E edges and where E greater than 3, the following formula holds, dot E is less than equal to 3V minus 6. Okay. Before I say how to use it, first I will list down all the corollary first. So if G is again a connected planar graph, okay, then G has a vertex of degree not exceeding 5. And then the next one is the similar condition with one more sufficient condition, which is n and no circuit of length 3. Remember what circuit? A path that end and start at the same point. Length 3 meaning 3 edges. Then E is less than equal to 2V minus 4. Okay. So how are we going to use this statement? You should think of the contrapositive of the statement. Contrapositive. So if P is violated, then if Q is violated, then P is also violated. So if P, if you forgot, just remind you, if P, then Q, which is logically equivalent. So if not Q, then not P. Okay, so not P is the one that we aim for is not planar. Okay, so if this inequality doesn't satisfy, then our graph is not planar. Okay, so for example, so let's pick an example, K5. I think we haven't shown that K5 is non-planar using the diagrammatic method, but we will see it using this corollary here. So remember what's K5? K5 is a complete graph with 5 vertex. So this is non-planar. Why is it non-planar? What's the number of E? What's the number of edges? 10. How about number of vertex? 5. So what is 3V minus 6? 9. 9, yes. But 10 is greater than 9. So E is greater than 3V minus 6. So K5 is non-planar. Okay. Because it is connected, okay, every point is connected, and it is simple because there's no multiple edges. So it must be non-planar. Okay. Corollary tree will be useful to show these K tree. Maybe I like this. So remember what's K tree? The complete bipartite graph. Okay. Remember that do you remember last time we showed it using the diagrammatic method? I say there's 3 regions. Maybe I just recall it for you. So last week we say that, okay, K33 is non-planar because if I use the graph isomorphism, okay, and then I can decide where the last vertex can go. Okay, there are 3 regions you can go, but every region you cannot avoid edge crossing. Okay, so it's non-planar because it doesn't emit a planar representation. So today we will use the degree of the number of edges and vertexes to see that why it is not planar. Okay, so what's the number of edges? Anyone know what's the number of edges of this complete bipartite graph? Anyone know? What's the number of edges? 9, right? Okay. E is 9. V is 6. Okay, so what is 2V minus 4? 8. Okay, but 9 is greater than 8. E is greater than 2V minus 4. And it also doesn't have, it is connected, okay? Because every 2 points are connected by a path. It is simple because every 2 points doesn't have multiple loops. It doesn't have circuit of length 3 because if you have a circuit of length 3, then this graph is not bipartite. Okay. Hence, it must be not planar. Okay. So these 3 conditions satisfied, then it must be this is not satisfied. Okay. Hence, 3 is non-planar. Okay. So I think we won't prove these 3 because I don't think we have time. But you can, if you are interested, you can go and look at the proof in the textbook. It is not hard to understand. Just use the formula, handshaking lemma, and the Euler's formula, and then you can get these 3 these 3 corollary here. Okay. So up to here, let's summarize a bit. Proving a graph is non-planar. To prove a graph is planar, you can just play around with the graph isomorphism and then remove all the edge crossing. But to prove a graph is non-planar, we have few methods to see. One is to use the diagrammatic method, like what we did at first. So you try all the possibility and see that you can't avoid edge crossing. Okay, so that it can't emit a planar representation. Okay. Two is you use the contrapositive of the above corollary. Okay. Corollary above. Above. Corollary above by looking at E and V. Okay. Okay, so there are more methods to come. So we got a third method. Okay. Up to here, any question or not regarding the usage of the corollary? No? Okay. So next we will do the third method. Okay. This is what I always say about topology. So this is topology. Right? Okay. So it's got some slight touch on topology. Okay, so what we're gonna introduce now is called an elementary subdivision. Subdivision. So what do you want to divide? Okay. So we want to divide there's nothing much to divide, right? You can't divide a vertex. So what do you if you divide the vertex, it's like you cut the watermelon into half, but vertex is already like the simplest, like the atom, okay? Simplest entity. So what we can cut is the edge. So elementary, I give you the picture first, and then I will say the precise definition. So let's say you got an edge from U to V. Okay. So when we say elementary subdivision, meaning we can cut this edge into, we can cut into half is not accurate, but I will lie a bit. So I just say cut into half. So you can put another vertex in between U and V. Okay. So you cut this edge into half. And then you can keep going on. You can cut this edge further. Okay. And then for how, no matter how many times you want. So this is the subdivision, elementary subdivision. Okay. So the precise meaning is you can remove the original edge. Okay. Remove an edge, UV, and add a new vertex W together with two new edges. Okay. Formally, you can set it, but you can imagine that you keep cutting the edges. Okay. So far, so good. So far, so good. Everyone following? Okay. If you're not following, later you won't see the picture. Any question or not? Up to here. Subdivide the graph, meaning you can cut the edge. Okay. Okay. So next, we will say that the two graph is isomorphic. Sorry, isomorphic. We already said it before. It's called homeomorphic. Homeomorphic. If they can be obtained from the same graph. Okay. So how to obtain from the same graph? By a sequence of elementary subdivision. So in mathematics, whenever we introduce a new thing, we're gonna use it. So we only introduce elementary subdivision, so we're gonna use it here. So what do you mean by homeomorphic? Let's see an example here. Okay, so last time we say that a triangle, okay, a triangle can't be isomorphic to a square. Okay. Anyone remember why? Because what? Because the number of vertices is different. Okay. So to be an isomorphism of graph, you need to be a bijection on vertices. And then make sure that how the vertices is connected before it is how connected after. Okay. So it is not isomorphic because it's not cannot be a bijection on vertices. But the triangle is homeomorphic. Okay, let me put this notation here. It's only one line, one horizontal line. It's homeomorphic to the square. The square. Because you can cut one of the edges. Okay. So in this way, you can see that it is also homeomorphic to the pentagon. Okay, because you can keep cutting. And then you can keep going on. Actually, C to the power n. Okay. Yeah.
It's not isomorphic.
Cannot. Cannot. Because, for example, it's not isomorphic to this, but they are not homeomorphic here also. They are also not homeomorphic. Yeah, they are not homeomorphic also. So there's no relation between homeomorphism and isomorphism. Okay. Yeah. So you can see that under homeomorphism, more are considered the same. Okay. Yeah, more graphs are considered the same, but it's enough for us to deduce some useful result. Okay. So you can see that quite a lot of result we can study just using topology. Okay. So sometimes you don't need to see things too clearly. Nothing. Okay. Okay. What? Topology? What topology? Oh, yeah. I mean, this kind of operation is one manifestation of topology. I didn't give you the definition, but this kind of procedure or method is called topology. Yeah. Yeah. So it's like you can continuously change the graph. Right? Can you imagine or not? Not tautology, it's different word, it's topology. Yeah, it's different word, it's not tautology, topology. So you can think of like continuously changing the graph without breaking it. Okay. So you're like continuously changing the graph. Okay, but anyway. Yeah. Because you can also go back to one point with a loop. And can you imagine or not? Right? You can add another vertex and then you add another vertex. Keep going. I think this one is the simplest graph you can get. So everyone start from this. Everyone start from this graph here. Everyone start from this graph. This one we call a this is a loop at one point. Okay, so everyone start with a point and a string. I'm just kidding. Okay, so if you keep adding the vertex and then you get all the other cycle. Can you imagine? Can you imagine? What? Can you imagine? Okay. Okay, so you talk so much. What's the useful of this? So in the textbook, they give this example here. Okay, so these three are all homeomorphic because you can just cut these cut the edges into half or more than half and then keep cutting. But there's one powerful theorem here. So this is by Uratowski. So I at first I thought it's a Japanese, actually it's not. It's a Poland guy. Okay, so it's a Poland mathematician. So a graph is a non-planar if and only if it contains a graph, sorry, a subgraph, contains a subgraph that is homeomorphic to K33 or K5. Okay, so you need to take note of this if and only if. So if and only if is already similar to equivalence. Okay, so if your graph is non-planar, it must contain a subgraph homeomorphic to K33 or K4. If you happen to know that it contains a subgraph that is homeomorphic to K33 or K4, your original graph must be non-planar. Okay. Remember the K33 and K5, just now we showed that they both non-planar. Still remember the picture in your mind? K33 is the complete bipartite graph between three vertices, and then K5 is the complete graph with 5 vertex. Okay, so you should keep these two in your mind. So what? Yeah. Okay. Remember the picture? Okay. If not, maybe we just go down and see one example and then recall the picture again. Okay. So for example, figure 13 here. Okay. So look at this graph here. Is it planar or not planar? Okay. So by Krosky theorem, it is non-planar because you contain a subgraph that is homeomorphic to the K5. Okay. Note that it is just homeomorphic because there's more vertex here. So they don't agree on the nodes, but they are homeomorphic because you can just remove it by the elementary subdivision. Okay. So they are homeomorphic by the elementary subdivision. Huh? Repeat what? Repeat what? Subdivision. Oh, because this, first of all, sorry, A, B, J, C, H, G, K, I, okay, this here, and the edges together form a subgraph of G, okay, of G. And then this subgraph here can be obtained by elementary subdivision of K5 because you can just add J here and then you add K here and then you add H here. Okay, so they are homeomorphic because homeomorphic means they can be obtained from the same graph by using elementary subdivision. Okay, can follow? Can follow? You want me to write it down? I mean, write it down or can follow? Yeah. Uh-huh. J, you mean J and K? Yeah.
Compared to like that, if you have the another page.
Like
Yeah.
I to G. Okay. Okay. So wait. Okay.
let me back up a bit. Okay, let me back up a bit. Let me move this. Okay, actually my method is a bit different from this textbook method. I think they look at a different subgraph. There are two subgraphs you can look at. So let me, should I do put it here? Okay, so there are two subgraphs here to look at, right? So you can look at the outside one, or you can look at the inside one. How should I? Okay, maybe I just draw it on the top. Okay, I draw it on the top. So there's one subgraph you can look at is this one. Okay, one subgraph is this. Okay. Then the other subgraph is this subgraph. So definitely you want the star inside. Okay. But the outside one you can be a bit lenient. So you can pick the inside one. Okay. Okay. So this one is the one I'm talking about, but the textbook one is talking about the outside one. Okay. But both these subgraph is homeomorphic to K5. Okay. Because for if you can't see it, maybe can I try move it up? Yes, it cannot. So actually this, yeah. So for the first one, is actually this subgraph here, H, and then H can be obtained from K5 by elementary subdividing GC. Okay. But for this one, for the second subgraph here, so let me put 1 and 2. For the second subgraph here, you are elementary dividing BC, IG, and GC. Can see it? Can see or not? Okay. Yep.
Assume that the number of pages also equals one.
Yeah. Every time you subdivide, yeah. Why suddenly you want to count the edge? Oh, just gradually. Okay. Yeah. Every time you cut it, you will add one edge. Yeah. That's right. Okay. So this graph is not planar because you contain a subgraph that is homeomorphic to K5. How about this one, this graph here? If you play long enough, or you can see it, actually there's a K33 hiding inside here. So there's a K33 hiding inside this graph. But how to see it, you should study this, how they're connected. And then you will see that K33 actually is hiding inside this graph. So that this graph is not, it's non-planar. Okay. So what's the moral of the story? But every non-planar graph that should contain these two subgraphs. Okay. So this means these two are the basic non-planar graph, and all the non-planar graph should be built out from these two. Built out from these two. What do you mean by only these two? What do you mean by that?
Other than K5 and K33.
Yeah. So then, other than K5 and K33, these two are not K5 and K33, right? But they are non-planar. But what I mean is, every non-planar graph should have this K5 or K33 hiding inside. So it's like building up from this. You mean if you consider less vertex and then different graph, is it? Are they non-planar or what?
Because now we only mention about should have K3.
Yeah.
There other than that. Should have.
How can we be so clear? Just building on K3 and K5 come up with a
Oh, you need to call this column guy. I mean, this one is study under homeomorphism, okay? In the world of homeomorphic or in the world of topology, you can see using K3 or K5. Maybe you see in other way, you can use different graph to see it. Yeah. But at least in this world of topology or this homeomorphic world, K3 and K5 is enough to see non-planar graph. Okay. So how to see it? You need to call this column guy. I think this proof is out of the scope of this lecture. Yeah, proof of this theorem is out of the scope of this concept. Okay. Any more questions? Any more questions? No more questions? So far, no. Okay. So let's take a break until 10:05. We will resume at 10:05. Huh? Mm-hmm. Yeah. 5H.
I think you say it's not homomorphic. I don't think. And I think
It has add 2H.
因为我刚才有问你，就是我们 subdivision 会加一个 h 嘛
Yeah.
我这个可不可以理解为，因为它加两个 h， 所以它就不算是
不能，它是它的那个它的connectivity 不同。你看啊，这边啊，你能够去掉的东西不是这个点哦，你可以去掉这个点，因为它是一个线，然后加一点。OK， 所以这一边，应该这样写。这一边的话，它可以变成什么？它可以变成这个东西，它也可以变成这个东西，但是这个是最简单的东西，你不能够再减少。OK 啦，你讲，你看这个也是3个 h 啊，你看3个 h， 但是它的点变成2个了，它点不一样。呀，因为你可以想这一个成这一条线加一个点，所以 elementary subdivision 你可以来退后想，就是你也可以加点，你也可以把点拿掉。
可以把点拿掉吗？
对呀，因为你看，因为这一个是从这一个加一个点出来的嘛。你看是不是？你自己想的是不是？你想一个是不是？
那个这个啊，是吧？
没有这个不等于啊，这个
不用再多加一个吗？
可以啊，再加多一个就是它啦。我只是说这一边的话，我加一个，再加多一个我就变成它了。
这不能拿来点是吧？
哪一个？这个？
啊，
这个可以，这个可以再简化，去简是这个，可以简到这个。
哦，
所以你看，最简化，你可以看到这个2个是不同的东西。
所以老师那个 elementary subdivision 我们不单只可以加点，我们也可以减点。
如果这点不能减呢？
那你讲减呢？看你讲减，你不可以随便乱减，你不可以说我把这个减点掉，我不可能啊，因为 side element division 只 allow 你在一条线上面做东西，它没有 allow 你在连着东西的时候把它弄减。所以你要小心一点啊，不要乱减你的点。
可以变到是这个，
不可以。
一条线这个东西
你放个点就是多一个 h 还有一个 vertex 嘛？
哪一个？
就你做一个 division 是多一个 vertex 还有一个 h 是不是？
对。
这个 edge 又多一个了。
啊，对，
条线上，
我在条件。
老实说就是从一条线上做东西。
OK，或者说你的elementary subdivision 不能够 increase，你要另外一个看法，它不能够 increase degree of vertex。你看它这个 degree of vertex 是3 ，OK， 但是你怎样 increase 你的 elementary division，你不可能 increase 你的 degree of vertex， 你不能加线进去。
哦，我们不可以，就是说我们不可以改它原本的东西，我们只可以在
对
线上做。
对，对啊，
对，这个就是
你不能够
就是
变它的
改掉了。
degree of vertex，所以它 degree of vertex 不一样，所以你就你拿这个好看。
在线上，然后写下来的。
这个就是那个
Yeah，
homophobia 啊，如果
后面 morphic
哎，
没有，后面 morphic to 这个 star， 还有旁边还有那个
做还有那个
才是那个 complete graph。complete graph 的话是你每一条线每一个能够连的线你都要补进去。
就它本来就有
就是不是讲每个连的线都会补，就是你要每一个 vertex 都要连到。
哦，
对，每个 vertex 你要放去哪里？刚不完。你要什么？
就是
你告诉我。
那个图可以翻一翻。就是它 v 等于
那个是往前推哦，你记得吗？If P then Q， 如果 Q 对的话，P 不一定要对的嘛。
什么？
记得那个 statement 嘛？If P then Q， 你现在查的是 Q 对不对？对不对？
对，就查。
你看 Q 如果是 true 的话，P 可以 false，P 也可以 true，还记得吗？所以你不能够这样查的，只有 contraposition。
那这个样子。
这个咯，用那个 Kurosky theorem。
他说这两个图是就这个的 implicit， 我看不出来啊。
对，你看不出来，你要去试下去移它，你要去找那个 subgraph， 找一个 K33 在里面，我可以画给你看，如果你要的话。你看它这个 F 画到1，不是你就 F 画到1哦。F 画到1的话，它从哪里过去？它应该是从 A 过去，这样子。F 画到1，按到1到 J，1到 J 应该是这条。对，然后你就到1到 D， 还有到 D 这个，连一个，然后1到 F 到 H，F 要到 H，F 到 H 应该是这个。这个 F 到 H， 然后 F 到 I， F 到应该是要到 D 要到 E 已经有了 ，D 要到 I，D 要到 H， 我觉得它应该是经过 C， 所以应该是J 要到 E 有了 ，J 要到 I 的话是 A， 应该经过 G， 它应该经过 G， 所以要经过 G 然后回来。J 到 H，J 到 H 应该是这条，所以它就长得这样，可以吗？
老师到这种程度走，就是讲流。
就这样弄，就这样弄等下我给你们做tutorial。你们全部人第二个问题就是，如果考试这样的话是，
老师就不看了。
老师就不看了。
我可以问你是怎样看它里
哎，这个容易看，这个比较容易看，
这容易看。
这个不了
可是我
难看。
可以问一下你的看的顺序是这样吗？
没事，我只要把这 K5丢进去看就出来。
我的看的方式是，
你看，
现在是 K5在这里，这一个是一个 graph 吗？我要找它里面的 subgraph 是跟这个 isomorphic。homeomorphic，OK，我就会，因为你在 K5 长这样，我就大概找出刚才你画出来给我们看的那个，然后再从这里加点上去它，这样子它就可以成。
对啊，那个就是 homeomorphic 的意思啊，加点的意思就是上，
所以它加点是可以加在 K5，可以加在 K5 上面。
可以，没有，它只要是从一个最简单的东西加上去，对吗？
这个也是加上去的，
所以他们
是
不是这样？
不是，这个是 subgraph， 你要记得这个是 subgraph。我们只要先看 subgraph， 然后再看它怎么变。
我可以，
你看，它加的点在这个 A 这边，加在 G 这边，加在 C 这边。
我可不可以理解成这个其实都是从一个点然后一个圆出来，像你刚才讲的东西。
不一定。你看这个就不是从点跟一个圆出来的东西。
哪里一个？
在这个 我给了这个 example， 这个就不是从一个点跟圆出来的，这个是这个最基本的东西，不一定，看它最基本的是什么。
这一个是哪里一个的最基本？
这一个不是从这里变出来的，
对，
这个可以变成这个，对吗？不同的东西变成不同的东西，对，是吧？
如果我的 line 那个 H 嘛是 versus 这边 A 去在这边 B 我的 elementary subdivision 我可以除掉这个吧，可以弄走这个点。
不是，它的除掉的意思是说你要做模，你要做。
刚才老师说可以加可以减，
没有，你的减你要小心一点，就是你要知道什么时候。
如果
就是减不是一个 operation， 减是一种看法，就是因为它从同一个东西来，就是从这个东西来，听明白？它从同一个东西，
就是说如果减是往后看的
对，
现在要做的就是向前看，
都可以，就是看你要怎样。
没有没有，因为我们现在没有一个 precise 的向后看的东西，所以你没有讲你只能向前，你可以 formulate 一个向后看的例子，但是我现在是说你要小心，因为我们没有一个 precise 的，你可以去 try formulate 一个向后看的，你可以，但是我现在没有，我就想不要就小心，我就小心，我没有讲不可以，我没有讲不可以，但是要小心。你要的话，你就去 try to formulate 一个向后看的，什么时候可以把点拿掉，你就要去把它 formulate 出来。我没有讲不可以，但是要小心，因为我没有讲这个东西，对不对？OK， 好，testing 1 2 OK，let's start。Okay, just now,什么 point correct 是一反啊，是叫什么？忘记了，叫什么？忘记了。乐器，OK， yeah， 乐器，Okay, just now Yiqi asked about this one, right? So how you see this K33 as a subgraph of the subgraph? So I try to trace it out here. Okay, so this is the subgraph. Okay, I put this dot here because we know that this is bipartite, so we can label above with one color and then bottom with the other color. So this is the maybe make a bit more apparent which point is it. Okay, so this is the subgraph. This is how K33 is sitting inside here. Okay, so it's like quite convoluted. Okay. But next week got some tutorial question where you can try and play around and see. Next week, yeah, next week. Because this week was last week tutorial. From last week, tutorial last week. Okay. You can go try and play around with this. Okay, next. Next is the graph coloring. Okay, graph coloring. So what we are concerned with graph coloring is, for example, I give you a map. Okay? I give you a map here. So how many color do you need to fill the adjacent region with distinct different color? Okay. So for example, if you put blue here, okay. So these three should be color different than so A, C, D should be different color than blue. So let's say we put A as red, okay. But C is adjacent to B and A, so they have to be different color than two of these. We will put green, okay. And then D touches these three, so maybe we need another color. Maybe we pick orange, okay. And then you keep going on, and then see what's the least number of color that you need to color, okay. Of course, you can put 1,000 or 100 color in, but that's not what we want to look for. We want to look for the least number to color the map. Okay, everyone got it? Okay, should got this question first before we continue. Otherwise, you will definitely not. Okay, everyone got the question? What's the least number to color the map with the adjacent region different color? Okay, so yeah, attendance already. Just stop. Okay, so if you imagine, okay, this whole piece of land, okay, you string to one point, okay, you string the connected component to one point, the length to one point, okay, and then whenever they share a boundary, you draw an X, okay. So actually, this you can produce a graph, which we call the dual graph, okay. So this is the dual graph, okay. So in this case, coloring of the map or the land become a coloring on a vertex. So vertex, adjacent vertex have to be filled with different color. Actually, we encountered this before, which is the, who remember? Huh? Don't know name. The bridge, yes, the bridge, 7 bridge of converge. Yes, the bipartite graph, okay? So bipartite graph said you only need 2 color to color the different 2 partitions of the vertex, okay? Bipartite graph, okay? So in that case is 2, okay? But now you are looking at different graph here, not bipartite anymore, okay? But it's a planar. I think it's a, I'm not sure it's planar. Okay, never mind. Okay, so let's look at this map here, okay? So how many color used to color the map? Huh? 4. 4. So it's like 1, use what color? Better. 1, 1, 1, 2, 3, 4. Okay, but some of you say 5. Okay, because the C is a okay. But anyway, huh? What? Actually, same color, sorry. So where's the fourth color? Australian? Okay, yeah, correct. So 1, 2, 3, 4. Okay, Australia is India. Okay, so but anyway, but actually there's a theorem says that you can color using 4 color. Okay. But this one they prove blue because just to show you that there's an option. Okay. Okay. Next. So we define a coloring of a simple graph is the assignment of a color to each vertex such that no two adjacent vertex are assigned the same color. Okay. Only this we call it a coloring. Okay. So if you imagine that if you have a map and then you just color the same color, so it's hard to see, right? Right. It's hard to see if you don't notice the boundary. But if I color it differently, then without looking at the boundary, you just look at the color, you know, the region only. Okay, that's why we're interested in a different color at the adjacent vertex. Okay. So next, we define what's a chromatic number. So chromatic is something to do with color. Chromatic number of a graph is the least number. Okay, it's the least number that you use to color the graph. So this is exactly the solution to our question. Okay, chromatic number is the solution to our question. What is the least number of graph coloring? Okay, so chromatic number is the solution to our question. And there's a four color theorem here. Okay, four color theorem meaning if you start with a planar graph, okay, we already know what a planar graph is. There's no edge crossing. Then the chromatic number is no greater than 4. So you can use less than 4 color to color your planar graph. Make sense? Okay, this is the proof of this theorem also out of this talk. There have various ways to prove it. You can use simple stuff to prove it. You also can use very high technology stuff. Okay. Okay. So this one you should take note how to show how to find the chromatic number of a graph. So first, to show the chromatic number of a graph, you should show that the graph can be colored with k colors. Okay, this means that your chromatic number is less than equal to k because chromatic number is the least number you need. But you already color with your graph as k number, so k is greater or equal to the chromatic number. And then the next thing is you need to show that the chromatic number is greater or equal to k. So that means the graph cannot be colored by using fewer than k colors. And altogether you will have k greater or equal to the chromatic number and greater or equal to k, which implies that your chromatic number has to be k. Okay? So this is the strategy. Okay? I will show you how to use it. Okay? Don't worry. So for example, in G here, okay, we want to show that chromatic number of G is 3. Okay, so first we need to show that you can use 3 color to color this graph. Okay, so let's say A is black. So we can put B is blue. Okay, E. Maybe okay, if B is blue, then since C's connect to B and A, so C has to be a different color than black and blue. So maybe we put red. Okay. D connects to B and C, so we can put black because there's no contradiction here. How about E? E is connected to D and B. We can put red. Okay, good. F, we can put blue again. Okay. And then G is black. Can be black. Okay. So this shows that three color is enough. 3 colors is enough to color our graph, which is means the chromatic number is less than or equal to 3. But how to show that 3 is less than or equal to chromatic number of G? Okay. So if you remove one color, then you cannot make sure that the adjacent vertex have different color. Yeah. So if you remove, for example, you remove blue, okay. If you put black here, then there will be adjacent vertex with the same color. If you put red here, there will be adjacent vertex with the same color. Or you can say that there's a triangle here. Okay. Once you have a triangle, the chromatic number have to be greater or equal to 3. Right? Because if you have a triangle here, these 3 vertex must have the different color. Clean way to say Seng G as what? As a triangle sum. Okay. Okay, how about H? H also the same. So we put B as blue again, C as red again. Now D black, E red, F blue, G black. Can G be black? Why? Okay, it's connected to A, so it has to be different from A, different from E, different from F. So we need to pick a extra one. So maybe put what? Why? So the chromatic number is less than equal to 4. Okay. But why is it greater and equal to 4? Why? Yeah. Why have to be greater equal to 4? Why is it greater equal to 4? 3 is not enough. We can go extra. Oh yeah, something like that. Yeah, you can say that. Yeah. So if you remove one color, then you can see that there are 2 adjacent vertex which have the same color. Or is there any way to see? You can say that. Let me see. Let me see. That's all, huh? It's okay. It's fine. Yeah, I was trying to say something else. Okay, never mind. Okay, we will say when the times come. Okay. Okay. So there are few chromatic number that you can find. For example, if you look at the complete graph, okay, if you look at the complete graph means you have n vertex and then all the vertex are joined by an edge. Okay, so these are the example of complete graph. And then the claim is the chromatic number of complete graph is n. Okay, is equal to the number of vertex. Okay, because every vertex are connected, so that means every vertex have to be different color from each other. Okay, because every vertex are connected, so you need to make sure all the vertex have the different color, and then you can show that there's enough to color it out. And then how about bar-Patak graph? Okay, complete bar-Patak graph. The chromatic color is 2 by the theorem of the bar-Patak. And then the chromatic color of a cycle is depend on how many integer you have. Okay, it is 2 if the n is even, it's 3 if the n is odd. You can look at this example here. Okay, try to work out a few examples to see. So if you look at the triangle here, so you will fix the first vertex as yellow, second as blue, as red, and then the third one you can't put yellow again. Okay, because otherwise these two yellow will be the same. So you need to add an extra color in. But it is okay for even because you can do like yellow, red, and then you should from this example here, you should work out the general argument why you need 2 for even integer and 3 for odd integer. Okay. Okay. So what's the application of this graph coloring? You can use it to schedule your final exam. Okay. So that if you put if you put different color in different day, so that you won't have the same different exam at the same day. Say the third time. Yeah. So so if you go and see my lecture recording, right, I repeat the same story basically 3 times. Not creativity. Wow, I need to count with 3 jokes. Okay, I'll try again next time. What?
Three different jobs for
Different jobs?
scheduling jobs.
Jobs?
Yeah, for class.
Job for class. Scheduling the shows. Okay. And then because some of you come to my Monday class, right? So they asked about this. Actually, this question appear in your textbook question. This is actually the textbook question. Yeah. So some of you come to my Monday class and then ask about this out of my preparation on this. So this is actually in your textbook as well. This question. Find the chromatic number of the wheels of wheel. Okay. So find the chromatic number of wheels. So you can go and try and color the wheels, and then you should see that if the wheels have even. So there are 2 ways to see this. Okay, I don't want to say the other way. So let's just talk about this conjecture here. So the chromatic number of Wn, okay, Wn means you got n vertex and then add 1 dot in the middle, is 4 if n is odd, is 3 if n is even. Okay, and then I already checked that this is the textbook answer. Okay, but you can show it. This one we write conjecture is because we on the spot go and check and try and work out some pattern, and then we see that maybe this pattern will work, so we conjecture this. Okay, so you should go and prove this. Okay, so try and color it, and then try to show this. This is the tutorial question inside your textbook. I think it's one of the odd number, but they didn't give the step, so you should try and argue. If you can't argue it, try at home. You can come find me. Okay. Okay. Any question? Any question before we move on? Graph coloring. I think this is the last part of the graph. I think. Huh? What? Huh? 3 and 4. About this one. What do you mean 3 and 4 about it? No, I don't count the extra. Yeah, depend on you. I think this is the textbook convention, right? Is this the textbook convention? Yeah, okay. Yeah. Okay. So the n here is always n plus 1, n minus 1 vertex here. Huh? Cycle at 1 point, yes. That is how you should think of wheels. cycle at one point. Okay, so this is just the number of cycle, and then you need to get one. So you got n plus 1 vertex. Okay. Yeah. Any question? Blur. I think if you blur, you will continue to blur. But now is the time you can come back now because it's new now. Okay. Okay, if you want to come back now, you can come back now because we talk about trees is a different subject for those who are confused. Okay. So okay, now we talk about trees. Okay. Okay, Christmas trees. Okay, you can think about Christmas trees. You also can think about coconut trees, durian trees, banana tree. Huh? No, it's not phrases. Okay. So what's trees? So trees basically are connected, undirected graph with no simple circuit. So we don't want the leaf grow back to the stem or grow back to the root. Okay, that's weird. So I draw some example of tree. I think this one quite looks like tree. And then this is also a tree, connected, undirected, non-simple circuit. But the third one is not a tree. Okay, because you got a simple circuit here. Okay, so these are the trees. Yep. I think you can. You also can have a directed tree. You can have a directed tree, but we try to be as general. Yeah, okay. You can put direction in, but yeah. Yeah. Hey, so you have you guys learned about biology or not? No, little bit. So there are two directions in the trees, right? So one direction is sending the food from the root up to the leaf, and then one direction is sending the carbon dioxide and from the leaf to the whole body. Yeah. So there are two directions in the tree. Okay. Okay. So yeah. Okay. So the next one is so you see that actually this definition is quite simple, right? But actually you can deduce one consequence from this definition here. So you can see that and the undirected graph is a tree if and only if, okay? Remember, if and only if is somehow equivalent, there's there's a unique simple path between two vertexes. So meaning you pick any two vertex in the tree, there's a unique path to go. There's only one way, and it's unique. Okay. And it is simple, meaning there's no repeated. So it's not like come back and then go forward, something like that. There's no multiple edges in your path. So there's only one way to do it. Then this is called a tree. Okay. So meaning tree is actually a very efficient stuff. Okay. Very efficient. Efficient. Huh? Very 死板. No, very efficient. Very efficient. Okay. Life need to be efficient. Creative and efficient. Okay. Okay. Yeah, creative and efficient. Hmm? Yeah. Different correction. Yeah. So I mean, if it is directed, then these two path is different, right? Because one is going forward, one is going forward. But if undirected, then these two are multiple edges. Okay. Okay. Because not the same, right? One is going forward, one is going back. Okay. Okay. Next one we will talk about directed tree now. So which we interested in is the rooted tree. Okay. So rooted tree meaning we will pick one vertex as a root, and then all the other vertex are directed away from the root. Okay. So that's direction here now. Rooted tree. So how should you think about it? You should think of the tree grow from the root. Okay, but this root is just one point here. So for example, if you take this graph here, okay, so this is a tree because it's connected, simple, and then what else? No simple circuit. Okay. So let's say if I pick my root as B, again, so you can take this B out, take it out, and lift it. And then you think of this weight on these vertex, and then the weight will fall down. And then it will direct it away from B. And then it is furthest away from B if the length of path is larger. Okay. So for example, if you take C as a root, okay, then you will see that E is the furthest vertex directed away from C. Okay. Following? Hello? Following? Yeah? Okay. This one is sub tree, so remove it first. Yeah, in this three topics, right, there's a lot of algorithm and some terminology. So instead of writing, I just point out. I think it's better. Otherwise, repeat the same job. Okay, so if V is not a root, okay, then V will have a parent. Parent meaning the unique vertex that directed to V. Okay, so for example, you can see that if you are not vertex, okay, there will be someone above you. Sorry, if you are not a root, there will be someone above you, directed to you. Okay, for example, B, there's one vertex directed to you, which is C. So we will call C a parent of B. Okay, you can see that this graph is actually like the what do you call that? The genealogy. You can think of the genealogy of your family. Or your family tree. Yeah, your family tree. Okay. So here is your great part. Okay. Yeah. Okay. Oh, this is the Adam. Okay. It depend on your belief. Okay. So next. Next, okay. You got the parent. Okay, parents. And then next you got the child. So C is a parent of B, then B is a child of your parents. Okay, makes sense. Okay, B is a child of your C, of your parent. And then if you have the same parents, then you are siblings. Okay, so you can see that E and A has the same parents, so they are the siblings. Okay, makes sense. Okay, next is ancestor. Okay, what do you mean by ancestor? All the guy above you are your ancestor. Okay? Your 18th ancestor. Okay. So for example, who are the ancestor of E? Okay. Those that are what's that? Huh? Yeah, it's B and C, right? So it's B and C. So how do you explain it? So it's the path from the root to E. Okay. All the guy all the way from the root to E. Yeah, your parents also ancestor, correct or not? Correct, right? Correct. Yeah, your parents, your ancestors. Yeah. Okay. And then how about descendants? Okay, descendants. So it's all the way from you to the we have no leaf. So what's the word they use? Are those vertexes that have V as an ancestor? Okay. So what's the ancestor of B? descendant of B, that means all the vertex that have U as the ancestor. Okay, so everything below U is your descendant. Okay, because they have U as your ancestor. A bit twisting. So descendant is those vertex that has U as the ancestor. Okay. So what's next? Leaf. Okay, the next one is leaf. So leaf meaning you have no child. So who have no child? The one that is the outermost vertex. They have no child. So we call it a leaf. And then if we call this leaf, how do we call this? So if you don't have child, we call you an internal. No, if you have a child, we call you an internal vertex. It's stay inside internal. Internal vertex, huh? What verticals? Inner verticals? Inner vertex or inner verticals? Vertexes. Yeah, vertexes. Yeah, vertexes is a plural, right? So vertex is yeah. Why flower? Flower is also outside. Internal vertex, okay. So you call it internal vertex, okay. So one thing you can see here is either you are internal vertex or either you are leaf. Okay. So leaves and internal vertexes partition your vertex set. Okay. So either you have a child, either you don't have a child. Okay. So the union of these two is your vertex set. Okay. So internal vertex and leaf partition your set. Did I put a remark here? Yeah. So leaf and internal vertex partition your vertex set. Okay. So let us recall again. Sub tree later. Later. Okay. So recall again. What's the parent? Parent is the unique vertex that directed to the vertex if the vertex is not a root. So everything that is not a root should have a parent. Correct or not? Does everyone have a parent? Yes, right. Okay. Otherwise, where are you? Huh? Who is single parent? Oh, C. Yeah, C is the root. C is the root. Yeah, C is the root. So C has no parent. Okay. And then ancestor is all the way from the root to you. Okay, the path, all the vertex in the path from the root to the vertex. So the ancestor of E is all the way from the root, all the vertex, all the way from the root to E. Siblings have the same parents. Child of B, because B is the parent of E and A. And then descendant of C is all the vertex that has C as the ancestor. Okay. Okay. So Chinese say, okay, I don't want to say. Maybe later a bit a bit rough. Just say. No lah, I mean this one descendant ma. So who are the descendant? As long as no, that's okay. No, I mean like but I mean as long as the okay, never mind. Okay. Never mind. Okay. So okay. So E and D, EAD are the leaves, and then BC are the internal vertex. Okay. So these two partition the vertex set. Okay, finish already. Okay, one more. So sub tree. So sub tree. Okay, so what's the sub tree is? First of all, sub tree is a subgraph of the tree. Okay, but you want to include all the descendants. Okay. So sub tree usually we will, because tree need to have a root, right? So sub tree also need to have a root. And then you need to include all the descendants from the original tree. Okay. For example, in this case here, so what's the sub tree at B? Okay. So a sub tree at B, you should start with B. Okay. And then it's a subgraph of the original tree. And then you need to include all the descendants. Okay. So if you just put B and then go to E, this is not a subtree. Okay. So subtree you need to include all the descendants. Okay, what you can imagine is you can drop ink here. So the ink will follow the edges. Okay. Yeah. So whoever get the ink is in the subtree. Okay. How many subtree? How many different subtree? So you can have 1, yeah, 2, 3, 4, 5. So actually it's depending on the number of vertex. How is 5? So 1, the whole original tree, and then 2, and then 3, and then 4, and then 5. I think it's depend on the number of vertex. The number of subtree I think is equal to the number of vertex. Because subtree you need to include all the descendants. So there's only one way to do that for every vertex. If you can have more, it's because of you can do something, some different definition of subtree. Otherwise, there's only one way only, right? Because you need to include all the descendants. If you're given 1 point, there's only one way to do it. There's only one way to do it. So, yeah. Not creative, huh? This definition. Sometimes it's not creative, not to say creative, because sometimes we want to use it. Okay. Any question? We will leave the algorithm to next week. Few algorithms. A lot of algorithms we need to learn up to the Boolean algebra. I think Boolean algebra will use less than 1 lecture to finish. So this graph one is really long. 4 weeks, maybe up to 5 weeks. Any question on trees or your family tree? 这是贞子啊，这贞子 M
also have combinations.
对
We also have combinations.
What do you mean by combination of trees? All 2 different trees. What do you mean by 2 different trees? You want to look at 2 different trees? 2 different trees is like 2 connected components, right? So yeah. So for now, we're interested in 1 tree. No, just now I was wanted to say, who are the descendants of C? As long as C can say, I'm your ancestor. So if you turn it into Chinese,
I get
you don't get it.
Maybe I get a bit.
You don't get it. I'm your ancestor. What's in Chinese? I'm your ancestor. What is Chinese email ancestor? No. They say, I think they say, 我是你的祖宗哎。或者我是你爹也可以。Anything like that. Something like that. 祖宗 better because further. Okay, ancestor, yeah. Okay. Any question? Any question? Any question? No? If not, huh? What? Yeah.
C is a descendant of C.
C is C a descendant of C? I think this is not reflexive, right? Descendant is what? Those vertex that have V as an ancestor. But C is not an ancestor of C. C is not a descendant of yourself. You cannot born yourself. Ancestor is the thing that is not, you see, so excluding the vertex itself. Okay. So ancestor path from root to you, but exclude you. And include the root, but exclude the vertex. Okay. We are not your ancestor. Translate to Chinese. Okay. Any more questions about these three? Yeah, this one is just some terminology. Next week we will use this and then try to do some algorithm. Any more questions? No? Okay, good. Okay. Now let's break until 10:58. One by one, you can come collect your quiz. And also, if Caleb or Jia Wei want to, okay, maybe later after we discuss the quiz, if you still want to look at your midterm exam, you can see after the quiz discussion. Okay, so every of you can like one by one come and find your quiz. Okay.
这个里面包放的，我眼睛还挺晒烂的。喂，晶晶，跟生病，佐证，东川，导致剩下这个不利。
Yes, yes, thank you. Hey. Ah. Huh? Yeah. Same. L 有可能在变成just take away the folding. Okay, line.
过了什么？
Not straight line. This
找到你了。
Including buildings.
yes. Okay, away.
Oh, that's nice.
No. So you say straight front, right? No, you go straight front. But you compute the straight front is different. Yeah. So why not just take away this? So royal flush is but we include straight front. How do you know about that? Huh? How do you know about that? Because I didn't introduce it, so I was curious by how you know about it. There we go.
Yes.
How you watch it? Yeah, because so we if Royal Flush is just for this one. I think this part is correct. I'll give from. Yeah, that's right. Like this one, okay. But this one, we just take away all the straight lines.啊，等一下我讨论水要平。哦，这个我可以给你们，等一下等一下我讨论水。啊，一样，反馈水要。是啊。不够。哎。对，关系，关系。啊，等下。啊，这我没有签，这都我在放不掉哎。这我不能放进去。别问他。要帮我打。我不会做。 你们两个没有签到对不对？
对，我也忘记了，应该是那时候是讨论那个我也来会有，我已经对，说是麻将用这种节奏，因为麻将我已经不想象。都是麻将，对面。
拿来哦，他们帮你拿来哦，对啊，包心意哈，啊，对，OK，谁？你在哪里？啊，他没有来，他是谁？啊，包心意啊，包心意怎么没有来？包心意，大家给我看一个东西，对。包心意，你认识吗？
I don't know 了。
不知道。看一下有没有？等一下，我看一下。你看一下有没有？看一下有没有？哪个？这个？这谁？放在哪一个？他嘞？他在哪？他没来。他干嘛没来？
这种中国的协会。
什么？我不知道。OK。没理解。偶尔抓一下。江。对。哎，罗英杰不是有来吗？罗英杰叫他来。叫罗英杰。你不太认识啊 ？Yeah。Hello， testing，罗英杰。罗英杰。王瑞坤在这边吗？瑞坤是你啊 ？OK。来，罗英杰。有 quiz。
再拿一个江志炫，
对，
江志炫，
你是江志炫？江志炫呢？
江志炫在住着。
哪一个是他？哦，那个，OK，江志炫。翁清兵来，你是王婉玲看，来，我刚刚才问了，李月琪，来。
这没有附加分是吗？
江左仪应该是，查一下，江左仪来。张一彤。
河的哪了？
对。卢伟奇跟Michael something，Michael MV，就是那个黑人。对，是那个人。那 FIFA 哈。Watch FIFA， you guys 是不是 ？Excellent。你是谁？吴伟杰啊？哎呦，你刚才不是很早就来了？啊？你刚才不是很早就在这里？没对。Hello, testing. Okay, let's come discuss. Let's discuss. Okay, discuss the quiz. So can I see how many one of you played the game before? Go like this. No? 1. Okay. 2, 3, 4. Yeah, very few. I think there's some correlation here because AIT got the highest average mark because those people got them. Okay, but anyway, not much different. Okay, not much different. Not much different. Just a little bit higher. Okay, so first, so in this game we care about 5 card patterns. So who assemble the 5 cards better, then you will win the game. So question 1 is the easiest one. How many combination of picking 5 cards from the deck? So we don't care about permutation. We just only care about permutation. Okay, use C. And then 1.2 straight flush. So it's a 5 card sequential in rank with all being the same suit. There are 4 suits here. So each of them have 4 suits. So how many combination here? It's just 10 times 4. Okay. So if you happen to use different way to count it, if I mark it wrong, then you should check whether you get the same number or not. And then see you calculate the right number. 1.3 flush is all being the same suit, but not including straight flush. Okay, so you need to take away 1.2 because this is the inclusion exclusion principle. Yeah, so you take away the straight flush. So how to compute flush? Just 13 choose 5. So within the same suit, you choose 5 number, 5 card, and then there's 4 color, 4 suit. You multiply by 4, and then take away 1.2. So if you compute the right number but didn't take away minus 40, I'll give you half mark. Later. And then if you compute the wrong flush but take away the right 1.2, then I'll also give you half mark. Okay? Because you know how to take away things. Okay? So next one is 1.4. 1.4, there are 3 questions inside here. I put it as bonus. So 1 is 4 of a kind. So meaning 4 have to be the same rank. Okay? And 1 random card. So for example, 2222A. Okay, 2222A. So there are only one way to pick these 4 numbers. Okay. And then there are 13 rank you can pick. And then what else? And then you can pair it with 48 possible number because 52 take away 4 is 48. So these are all the 4 a kind. And then full house is a pair with 3 of a kind. I didn't put definition again because I assume you can derive from the 4 of a kind because 3 of a kind and then a pair. So full house is like 3, 3, 3, 2, 2, for example. Okay, 3 of a kind, 2 of a kind. So there are 13 ways to pick the first 3 of a kind, and then they are left with 12 way to pick the pairs. Okay, and then for the 3 of a kind, you can pick either 3 number from the 4 suit. Okay, and for pair, you also can pick either 2 number from the 4 suit. Okay, that's why you take the product, use the product rule. Okay, next is the straight. Straight is 5 cards sequential, but not all the same suit. So what you can do is you have 10 possible straight, okay, each with different color, so different suit. So you have 4 to the 5 possibilities, and then you take away the straight flush again because you don't want all of them have the same suit. Okay. Any question on this part here? I think 2% earn my full bonus question. So one of them is William Edric. William Edric. Who's William Edric again? Okay, William Edric. And then one of them is Wang Rikun. And then Rikun. And then one of them is Zhang Jinghao. Is Zhang Jinghao here? Okay, King Hao. And then one, any more? Yeah, leave out anyone. One King Hao. Wait. Lo Yingjie. Okay. Okay. Next. Okay. Question 2.1. Okay, this question grew out from my lecture now. If you don't know how to do, that means you didn't do. So what kind of functions obey reflexive property? So first of all, why a graph is a relation? Because you can write it as x fx. Okay, that's the relation. Okay. And then what's the reflexive property for all x in the set? X have to be in the set. But xx is written in the form of xfx, so they have to be equal. Okay. Since this is equal for all x equal to x equal to fx. That's why you got fx equal to x. Okay. I saw that some of you confused with this notation, real notation, and the relation notation. Okay, don't confuse with these two. One is a bulk R, one is a capital R. One is a bulk R, one is a capital R. And then a lot of you draw this kind of picture, right? So this picture will depend on what set you pick. If you pick integer, you cannot join to a line. You just have this dot here, right? So you need to be careful where you pick your x. Okay, depend on where you pick your x, you can draw your graph. Okay, depend on what set you pick. If you pick a discrete set like integer, then you have like that. Okay, so depend on what set you pick. You don't simply just draw this graph for me. Okay, you need to write out what's your function. Fine. That fine. Any question? Any question? Any question? No? A question? No. Okay. If you have question, we can come back again. 2.2. Open-ended question. So is human relationship reflexive or symmetry or transitive? As long as you answer based on the definition, will be fine. The reason whether I can verify or whether I cannot verify, that's fine. But you need to follow the definition. Okay. For example, my answer say, if the human relation is reflexive, okay, if I say it is reflexive, then I need to argue that because everyone know themselves, so it's reflexive. So you and yourself is in the relation because you know yourself. But let's say if I answer, the human relationship is not reflexive because there's someone that don't know themselves. Okay? They don't know themselves well. Okay? So as long as you can find one counter example, then not everyone, you and yourself is in the same. Okay? Depend on how you argue. Okay? Some of you say that human relationship is symmetry because if I treat you well, the person will treat me well as well. I don't know if this is true or not, but I think this is a good belief, so you should keep doing it. Okay? The world better. Okay. So, and then I think I saw one is about transitive. Human relationship is not transitive. For example, the husband is good with the wife, and the wife is good with another guy. So it doesn't mean that the husband and the guy is a good friend. Okay. Not transitive. Okay. Yeah. So if transitive, then yeah, okay. Yeah, so max is like exploring all the possibilities. I think the world now is trying to explore all the possibilities. Trying to mix guy, female, and female, guy. Yeah. So yeah. So in the mathematics view, you will see it, but I think yeah. Anyway, yeah. Okay, any question? Any question? Any questions that you think you got a mark? Any question you want to ask before we jump into tutorial? Also return your tutorial quiz question paper. Yeah. No more question? No more question? No more question? Okay, so you can start your tutorial question, and then if you want to earn mark, you can come and find me, and then we will discuss tutorial question at 10:35. So just pick some question that you want to do, and then we will discuss all of them. Okay, yeah. Thank you. 2, 7, 5. Oh, but you're already full, right? Already full? Correct? Already full, mark. Yeah. Okay. This one you still want? You want it? Okay.
Yeah,
Okay.
can add mark, right?
Yeah.
Yes, like, okay.
Okay.
Thank you.
Yeah. Okay.
为什么这边之前没有打满？
啊，
对，但是我这边有显示说要拿那个水。
哦，你是其中一个，这个 R 跟这个 R confuse 的人。这个 R 跟这个 R 是一样的东西。
这不就是那个？
哪个
这样子。哦，
？Yeah，然后这个 R 呢？这个 R 也是指数。
这不是那个 relation？
对呀，我用一样的东西耶。
之前都问过这个问题啦。
什么东西？
老师你说的是就是看情况分析，就是我们还问过这个，我们还问过这个 Z 法要怎么区分？
但是这个没有，这个 R 跟这个 R 长得不一样，啊，是这样，这个 R 这样。
这里还有分哦。
对。
所以这个是实数的意思。
也不啊，
多加一个。
Yeah，就是
好的。
跟姐我可以给
好的。
1个小时吧。
那就留了。写中文就听不懂了，我一直在想这是什么意思。不能这样。没有了。
OK。Yep。喂。哦，啊 ，OK。
Also, this part.
Which part?
It's not possible because the right. It's not enough information.
This one you didn't explain why. Yeah.
So it's not right.
Yeah. And then this R also.
Yeah.
Yeah.
This is the mistake.
Okay. So now do you know why it implies?
Yeah, I know why it implies. I just didn't write it because there wasn't enough time. I already understood. My mistake was the R. Yeah, I just realized.
Yeah, as soon as you understand what I wrote here. Okay. Let me transfer 小哦。
跟你的答案是一样的。
哦，我看看这些，这个是什么？48，48，这个48，哦，对，我看看，就这个吧。
对。
520。这个你满分了对吧？你已经满了，对不对？OK，好，可以。
升那个语序。
哦，我也不知道为什么直接一分，应该我看算了，应该是。一点点，好， Okay.
所以这个其实是 x 的话是对的，做解释。
呀，这个是什么东西？我不知道。
好像我要写 x，
哦，你要写，
因为我这里的解释是
这么要写2次，我不知道这么要写。啊，这你懂了吗？
我知道。
这你懂了 ，OK。
如果是 x 的话，对吗
？OK。是表会上会上15啊，这是第好，这样
是可以一个方所以后面这边就是又抽出来了。
OK，
这2个
这2个啊，OK，这2个，
这样子，
这样子，OK，
One is cannot add.
没有，这个是 this question is about function and graph. This is not function. Graph. Just function.
Just this relation cannot be referred to as a function. 就是我们感觉这个东西，Just I remember in the slide. I suppose in the such.
No, this is not. I think this is not a function. I think it's not a function. This relation here is not a function. Because function meaning you input one input and then get one output, but this one what input output. I think congruence is not a function. Not a function. Because function you need to input.
Maybe we can write this in another way, just like 然后 equal to 什么这样的。That's maybe something like
For tutorial, you can discuss among yourself and discuss with your friend.
I think it is like a function.
Why?
Just this is the x and this is your output.
How about determining whether it's in the relation? Is it a function? To determine whether two numbers is congruent to each other, is this a function? Okay, maybe this single step is a function, but how about determining two numbers congruent to each other? Is it a function? You get what I'm asking?
I think
Like, is this a function?
maybe the equation not that.
Yeah, can you make it into a function?
Maybe transform it into letter form.
You can try and think. I don't know, but you can try and think. But for now, yeah, you can try and think. If not, then it's not a function. If can, then it's a function. Yeah, you can think first. You can think first. If you can think, you can get it, then you can find function. I can take you. Okay, go ahead. Huh? You want it? You still want it? Okay.
So this I don't get what point.
Oh, okay. Can. Okay.
我係硬拗分。
Your total score?
No, I mean
10.
oh 10.
Yeah.
他中一，我可以。
But what's your? Huh? You got enough? Yeah, you already full mark.
完了，再熬，我都没有付的，有点心痛。不会给我咩？我有剪出来诶。
有啊，给你1分啊。
1分够了，1分够。
够了，谢谢你，谢谢你。
太多了。
不是，主要是我也只可以拿1分，不是
2分
我拿2分就不太好意思了。
没有，我给2分哦。
那给我2分。
呀 ，Caleb 也是拿。
对，我这边也是有。
是
敲，不是你满分了就不用再掰了。
是敲
满分。
等下你不要盖住我们的脚位，等下脚。
OK，
好吧。我下到了。
你7分哦。
Thank you。谢谢你。
你这么拿2分啊？
是我最肯定。也做上去。
对，你刚给你 explain 了的吗 ？OK， 第一个是你这个写错了，对不对？这个 R 跟那个 relation 的 R 混掉。没有，这个是 set 来的吗？这个不是 relation 吗？这个 set 吗？这是 set 来的，这不是 relation。X in the set， 然后这个东西在那个 relation。
哦。
对啊。And then because it's the same X， 这什么东西来的 ？And then 这个是什么东西来的 ？reflexive 哦，刚才我写的看得懂吗？
看懂了。
啊，看得懂啊？要会写出来。
OK。
Yeah。
所以要写的话就是。
It's reflexive because 你应该要写 because XX is in the relation since S equal to FX， 然后 which means X FX is in the relation。
对，relation 要写在后面的。OK。对。那我开个档。
OK。
我这个是哪里扣的？
这个能扣1分，因为你这个搞混了。这个 real 是一个 set 来的，不是 relation。这个是 set 吗？
对啊，
这是 relation。哦 ，OK， 可以。如果你有写出来可以。然后我再看一下。然后这个我不知道你在做什么 ，because 什么这个，然后 then we know 这个，怎么会 because 这个 then 这个？
对，是属于一个那个它本身的那个。
对，这个我知道。
FX 就是我把它写成 Y 的。
OK， 好，你不要写成 Y 可以。
Y 也属于它。
然后我怎么？
因为 FX 等于它嘛，然后 FX 不是写成 Y 了。
那你这个不是
X 就。
这样，这个不是，其实我不用看都可以，我只要看这个就好了。然后下一步呢 ？dissatisfied 的，对你没有解释，你讲 dissatisfied 吧，你没有讲为什么？
要解释。
像我这样解释啊？为什么 satisfy？ 因为这个，然后证明这个等于什么？
其实我感觉这里的意思就是这里，因为就是 x 到 fx， 然后我把 fx 解成 y。
我知道，但是你要组织一下你的语言的。
哦。
当然了，当然，它全部这些对都是因为这个原因嘛，但是
要写明白。
对啊，你会不会来组织？
好的。
要组织一下那个语言。
前面这个我再问一下，就是这里只有10个，就只能到10勾圈，
然后要
不能再往下了。
不能，这个是我定的，可以往下，但是我这个规则定死的。
啊，行了，好，谢谢了。
OK。这个你有分吗？ 这个我可以给你分，因为你扣对东西，虽然你这个算错，你是周。
我以为还可以继续往下，然后就想
那个，
这个
你本来就5分吧，6分。
谢谢老师，谢谢。
OK，没事。
来，我其实没有什么，
没有啊，OK。
没有什么要问，但是我觉得终于，因为我看不懂，所以我一个都不对。
哦，
你看我为什么成这个？
也
因为我觉得它这个是有顺序的，
没有顺序，没有顺序。
所以我才
但是这个
也是啊，
这个我可以加分，因为你扣的是这个东西，
好委屈，
是吧？回去。
因为我不知道它为什么从哪里可以看到它没顺序的？
从哪里看得出哈？这错了。
就是英语的。
但是看不出的话，你也不应该去开。但是我
先后拿出来，先后拿出来也是一种拿法，我是这么理解。
我知道。或者说我后面有这个combination。
难说，真的。
怎么说呢？OK 啦，如果你真的要细究的话，我知道是有那个可能性在，但是呢，我该怎么说呢？我可不可以说？但是因为我看的是 combination，如果我真的是要他们顺着拿出来的话，可能我就要额外算。但是
没有办法。
但是呢，但是怎么样呢？呀，
这没有办法。
没事。
这理解问题不算数学吧？只能加一分。理解问题。
这种理解问题可以怎么解决呢？可以去看多一些东西，
很多问题怎么说呢？
了解多一点世界上的。
我很奇怪，有时候
懂吗？
真的，我看到就是我读完这些题，我就觉得它是有科学的，因为我就觉得它是这样。对，就是这个，这个是错的。
OK，
这个我也是觉得有科学，实际上就是思路就是没出来。
OK，
我以后做不对题了。我以后做不对题了。
什么叫做不对题？
因为我理解错的话，我做对了。
这只是一个过程啊，就是我以前小时候也是有这样的情况，但后来就慢慢习惯。我以前小时候也是有这种，就是每次会理解错题，就做你慢慢对你是写反了，但是看得出来是吧？
不会这样写。
我知道，
该怎么写？
但是至少就大的
反过来是吧？
但是可以了，明白就可以。因为你们之前是同一边的。对，明白。可以啊。
怎么样？
我以前不要讲以前啊，到现在都有时候还是会理解。 正常，这是正常。
一种不懂。
但是你应该怎样，你就应该可以试下看不同的东西。OK，
就这样。再看到下一个就好了。
下次加去下一个努力一点就可以下一个，下一个可以。
好，下一个可以。
可以。Yes。
这个算是一个方式。
那你解释 division 从一个方向给我听。
因为它可以分
整除的话，你像如果是整除的话，让那个所有的，比如说整除2的话，那如果是2的话，那所有的 f(x) 都是2的倍数，这个4。
那个OK， 这样子讲啊 ，function 是我给你一个 input， 你给我一个 output， 所以 division 怎样你接收一个 input 给你一个 output。当你要说 A divide B 的时候，怎样把这个表达成是一个方，所以是一个 function 从一个不知道什么 step 去另外一个可能另外一个 step， 然后可以解释这个 function。
就是这个就是 A 是一个方 ，A 是 S， 然后 B 就是 R。这个 A 是定 input 是定，比如说A 是2，然后 output B 的话，它可能是4、6啊这样。
那2怎么可以送到这么多东西？function 你可以把一个东西送去一个东西。One to many 不是一个 function。
那宇宙呢？宇宙怎么样？
听明白吗？一个东西不可以送去不同的地方。
或者我也是可以是，那我如果我让 B 是input 呢？就是
你说说。
我让 B 是6嘛，然后
你说看。
那 A。
你可以试试看。除非你可以把它说成是一个方程，除非。
就是这个是1对1的。
不是1对1就。
1对多也可以。
不可以1对多就是，不可以1对多就是，可以多对1。
多对1。我明白，这个就是说，我懂了。
可以啊。
对，
可以啊。OK。
那为什么上课讲的时候在讲这个reflexive 说的讲这个整除？
没有，这个是我去定一种 relation， 这个是其中一种 relation 吧。但是我把我的 relation 缩到 function， 哪一种 function 很主要是 reflexive， 这个是一种 relation， 这个也是 reflexive relation 但是我现在不确定它是不是，但是你还没有找出它是不是。
这个 graphs 是什么意思？但是
就是 graph 就是其实我就是想要讲这种东西就是这种 function graph 的东西。
那我这个 division 也可以画成图吗？
所以我就是要你来 argue 它为什么是一个 function， 除非你能够讲这句我还不清楚。
这个 graph 的方式是。
我的 graph 的意思是说，这种可以把它 get 出来的function。我不是那种 graph and tree 的 graph， 不是那种 graph。
可以画成这样吗？我定它，让它是我画一个 graph， 如果画一个
不 graph， 记住 graph 这个 graph 不是我们刚才学的 graph and tree 的 graph。
我知道。
OK，
就是画
这个就是 function， 其实我就是要指 function 嘛。我就指 function 嘛。
我可以画出来这个图吗？
你画。
如果我让 a 是2的话，那 b 可以是2、4，例如罚这样。
所以什么是你的 domain， 什么是你的 codomain， 然后这一个组合怎么跟这个组合是一对，对吧？把这一个表达成你呢？这是
这里
这什么？这上次的啊，
不是这次没？
这次的哈，
是啊，
这次我等下会讨论哦，这么
这个来这里，这里是一个 pub 嘛？
然后所以呢？
是不是？因为我看你的 definition 这里讲它要是
一样的
它的那个 vertex 是这样讲
然后怎么？
然后我就觉得这个它回到这个 B 的时候，这个 vertex 它是第2个 vertex，不是最后一个 vertex，这样子还是 pub 吗？
不用，你就 repeat 罢了啊。它这个没有讲要不一样或者不可以重复啊，你就继续罢了。
对，可以变。
都可以啊，随便。
OK，这样子哦，这个呢？哦，对，这个从
我会讨论哦，这么。
做吗？我一问到我就。
等一下我也是要讲的嘛。
我完全不理解，我就不用做啊。
OK，
这一个来到这里，然后然后他讲要去 B 哦，是这样子去啊。
可以啊。
然后再回到E 是这里，E 在这里，然后再回到 A 是这样子啊。
不可以，只可以一步诶，所以 E 没有到 A。
E 到 A 有啊，这里啊。
不能，它只要一条啊，不可以是这样子的。
什么意思到一条？
就每一步就一条啊。
每一个 vertex，每一 pair vertex 可以有一条。
要直接一条 H 连过去，不可以用连啊。如果你要这样子连，我就要写 EDA。不然的话这样不是没有差别了。
这样子哦，这个 A 来到 D，还有还要去到 B 哦，看这里。这样子我是这样子走可以吗？
不可以哦，这样子的话，你跟D 去到 B 和 D 去到 A 去 B 有什么不同？没有不同啊，没有不同。对不对？如果你说这个是 D 去 B，那我写 D 去 A 去 B，跟这个什么有不同啊？没有不同的话，这样什么东西都看不出来哦，对不对？
这是什么都没有啊？
没有了，不是一个概念。
Simple pub 是什么？是 Simple pub 是没有 direction 啊？
没有 repeat 那个 H，
没有 repeat H，
没有 repeat H，
所以有 direction 啊？
可以有 direction， 没有 repeat
H。那个 graph 不一样 ，Simple graph 是不可以有 direction。
不可以有 direction，yes，
undirected simple
graph。
simple graph 有 direction。有 directed simple graph。对啊 ，simple graph 是什么的？Simple graph 是 directed。undirected。然后 undirected 的，就像我们讲 undirected， 有5种 graph 嘛。第一种是 simple graph、multi graph、pseudo graph、simple directed graph、simple multi graph。directed multi graph，directed。所以 simple graph 跟 simple graph 是没有 direct 的，但是 simple pub 是可以有 direct 的。你看给我讲给我。
pub simple 的 pub 一样 ，pub 的 simple 是说没有 multiple。
但是不可以有 loop。loop 是 loop pub 是 pub。对，
没有啊 ，loop 是一种。
这样子 simple pub 可以有 loop。
可以。
simple pub
可以啊 ，simple pub 可以，as long as 没有 multiple H 啊，对，一个是
simple pub 是可以，
只要没有 multiple H。OK，
thank you。
Okay, let's discuss.
等一下，给我讲那个 length。这个 length。OK， 是这样，它是算 H 还是什么？算是人家讲的。
Okay, let's discuss 10.4.2.
Hello. Kopitiam time finish. Okay. So 10.4.2, Okay, let's see whether A, B, E, C, B is a path or not. So A, go from A to B to E to C to B. Okay, so this is a simple path. Okay, why is it length 4? Because 1, 2, 3, 4. 4 length. Okay. Part B. A to D to A to D to A again. Okay, so this is a circuit because you start and end at the same vertex. Length 4 because 1, 2, 3, 4. So it is not simple because you repeat AD and DA again. Okay, no multiple edges. C is not a path, but why? Because A to D, D to B. So there's no D H connecting D and B. Okay, so there's
Another path is that length that rightly is still
again.
is not path.
There's no path.
And the length is it directly divide 0.
No, no path is no path. Path 0 is like B, like B. Path of length 0 is the vertex. Path of length 0 is here. You stand here. So 0. Okay.
So for question C, we have to length.
No. No length.
Already.
No. No. No length. No path, no length. Yeah. Yeah. D also because A, B, E, C, B. There's no path connecting B and not path. I mean no edge. Okay, path you have path, but you have no edge. Okay, so the problem is edge, not path. Okay, it's edge. So B is not connected to D, so you cannot go from B to D. 10.4.4. I didn't draw the diagram up. You should go and see the diagram in your textbook and verify that if you pick every pairs, there's a path. So it is connected. 10.5.2 asks you whether there's an Euler circuit or not. What's the condition for Euler circuit? What's the degree of all vertex? All vertex has to be degree even. Okay. So you just go and check what's your degree of your vertex. So since all have even degree, you should find an Euler circuit. So how to find it is based on your creativity. Okay. So but by the theorem, you definitely can find one. So if you got an Euler circuit, you won't have an Euler path because Euler path, the theorem is what? What's the condition? If and only if you have exactly two vertex with even or odd. Odd. Because the odd degree will become your starting and your ending vertex. But all of them are even, so you won't get odd degree vertex. 10.5.2. So this one got an Euler path because there's exactly two vertex of odd degree. You can go and check. And that 2 degree is C and F. Okay. So your Euler path must start and end using these two vertex. Okay. The middle, how you go around is your choice. But you must start and end. Otherwise, you won't find your Euler path. 10.5.6. Also similar to 10.5.4, you got two exactly odd degree vertex, which is B and C. So your path must start with B or C and then end with B or C. Okay? Okay, go and try. 10.5.8. Okay, you can go and check all the degree is even. So you have an Euler circuit or path. Circuit, yes. So you can go and try. This one a bit harder, but not too hard. 10.5.10. Okay, so this one is another bridge question. So you need to find your connected component, find your vertex, find your so you can see that each vertex has an even degree. So you got an Euler circuit. Any problem with making this shrinking this blend into a point? No. Okay, as long as they are connected, it can be shrink to a point. Okay. Okay. And then I come across this 7 bridges problem here. Okay. So what's this 7 bridges? This is the Putrajaya. Okay, Putrajaya also got 7 bridge connecting. So Putrajaya is the government administration in Malaysia. It's a quite scenic place to visit. There's a nice what's that called? Nice garden. Nice garden. Because you know why? All the money in Malaysia going to Putrajaya. So that's why it's so nice. So you can go and visit. Okay. Anyway, next we got a 7 bridges here. So we have 7 bridges connecting this Putrajaya. So Putrajaya is here. So this is where the Prime Minister working. So we got 1. Okay, maybe I remove here first. So this is the Google map. So we got one bridge here, 2 bridge here, 3 bridge here, 4, 5, 6, 7. 7 bridges of Putrajaya. So the question is, do you have an Euler circuit? How to do? How many vertex you have? Vertex. Why got 5 vertex? 8 vertex. You need to regard the connected part as 1 vertex. Right? Okay. So all the outside one you can string to 1 vertex. And then the inside one you string to 1 vertex. Okay. So the question is like just 2 vertex and then you got 7 bridge. Okay. So in this case, 1, 2, 3, 4, 5, 6. So in this case, do you have an Euler circuit? Why? Because the degree is odd. So because you got odd degree vertex, so you have no Euler circuit. But do you have an Euler path? Why? Because they are exactly 2 degree with 2 vertex with odd degree. Okay, so you got an Euler path. Okay, so what does it mean to have an Euler path here? So that means when you do the Euler path, okay, if you start inside the Putrajaya, you must land outside the Putrajaya. If you start at the outside Putrajaya, if you walk the Euler path, you must end inside Putrajaya. Okay. What? What? Say again?
Through the river.
Stream through a river. Oh, okay. Yeah, stream through a river. Okay. Yeah. Okay. So if you walk the Euler path, either you land, you must start and end with the different spot. Okay. Okay. Next. Hey, no one get the job of all the money flowing to Putrajaya.
Right.
Okay, never mind. 10.5 with 30. Okay, I think only Sarawak or Sabah no. Huh? What? I mean the West Malaysia take all the money, give the KLCC. Yeah. Oh, never mind. It's okay. 10.5.30. So 10.5 to 30, there's no Hamilton circuit here. Because every circuit must pass through the ECF twice. Okay? because this one is similar to our lecture problem, lecture question, right? So if you use out these edges, if you want to do a circuit, you must pass through C and F twice. That means you need to make C and F double. No Hamilton circuit. This is about Hamilton. Hamilton meaning every edge passes once. And every vertex, sorry. Every vertex passes once. And 10.5.32, there's no Hamilton circuit because there's 1 degree 0. This one we also discussed it last time. Because if you want to do the circuit, you must passes this edge twice. That means you need to passes E twice. Okay. 10.5.34, this one a bit harder, but you also can see that because these are degree 2, so you need to include all these edges in order to pass through the vertex. But you can see that you have to do some passing twice the vertex to connect these two circuits. You should go and try. 10.5.36, I think there's quite a lot of possibility you can draw for this Hamilton circuit. You can go and play around with this example here. There's a lot of there's a few Hamilton circuit that you can draw. 10.5.38 also, you can go and try draw this Hamilton circuit. Okay, so the last one is to determine whether these two, not determine, but they tell you that they are planar. So try draw a planar representation of the graph. Okay, so you just move the edge crossing away. Move the edge crossing away. Then you can find the planar representation that you don't have an edge crossing in your graph. Okay, any other question or you want to go through? Want to go? Or want to go? Are you? Yeah, want to go class. Okay. So let's stop here. Yep. Yeah. Just hello. Just return me your quiz.